Welcome, everybody. I apologize upfront for starting with very elementary things again. For one thing, I didn't know what the speakers before me would cover exactly. And number two, um, maybe it's useful if every speaker actually uh, describes certain basic concepts in their own words. So here are some kind of very elementary facts. Okay, I'll write this fancy S for the unit sphere in Hilbert space. And I will now tell you what a density matrix is. Okay, so I start with, so this is not the easy road to density matrices. Okay, I'll start with POVMs. POVMs are positive operator valued measures. That's a family of positive operators. Positive operator means all the generalized eigenvalues are 0 or greater. So these operators are E sub Z, such that they add up to the identity operator in Hilbert space. Now, the main theorem about POVMs is this. For any experiment, any physical experiment, script E, that can be carried out on a quantum system with arbitrary wave function, there is a POVM E such that for every wave function, the outcome of the experiment has a probability distribution that's given by this expression, which is kind of the obvious expression that you can form from a POVM and a unit vector in Hilbert space. Okay, so the key fact here is, that's the most general kind of probability distribution that you could get with any experiment. It always comes from a POVM. So here's a corollary, a consequence of this fact. If you have any probability distribution over the unit sphere in Hilbert space, let's call it mu. And if a system has random wave function psi with distribution mu, then the outcome of your experiment, so now you do this experiment on your system with a random wave function, the outcome of the experiment, capital Z, as distribution, that's just the average of the distribution, what it would be for a particular psi, but now averaged over all psis. Good. So this integral over the unit sphere, that's kind of measure theory notation for, could be a continuous distribution or discrete distribution. So this integral in the discrete case would amount to a sum. We've seen this kind of sum already on other slides today. Okay, and now this expression, by doing some mathematical rewriting, you can write it as the trace of a density matrix times this operator Ez. Now, in my LaTeX code, I actually defined a command for density matrix because I wasn't sure whether I should call the density matrix rho or W. Okay, so I decided in the end for W. Okay, so it's the same thing as the rho that you've seen on other slides before. So this here, W, is the statistical density matrix, which is just the average of the projection to the one-dimensional subspace containing this particular psi. Now you average it over your random psi. Okay, so this automatically is an operator that's positive, has trace 1. Good. So now here the point is that the probability distribution depends only on the W and not on the mu, or it depends on the mu only through the W. So this means that if two different mu's, say mu and mu prime, have the same W, then they have the same probability distribution of outcomes. So now suppose you're setting up two different ensembles. In one ensemble, you create for every member of the ensemble, you prepare a particular wave function, but in such a way that it's mu distributed over the ensemble. For the other one, mu prime. Then these two ensembles have the same distribution of outcomes for every experiment. So if you hand this ensemble to somebody who can do any experiment they like, they'll be unable to distinguish between the two ensembles. Okay, they're empirically indistinguishable. Here are some examples of different probability distributions that have the same density matrix. One is with probability 1/2. So that's for a spin 1/2 particle, you take the up And with probability 1/2, you take the down state. Then your density matrix is 1/2 times the identity matrix. If you take with probability 1/2 the left and with probability 1/2 the right state, you get the same density matrix. If you take the uniform distribution over the unit sphere in Hilbert space, in this case, Hilbert space is just two-dimensional complex space, then your density matrix is just 1/2 the identity. So this illustrates that the mapping from mu to W is many to one. Different ensembles, different probability distributions can have the same density matrix. Now, for this simple fact, I think I should emphasize a kind of a basic consequence, a side conclusion of this fact. Suppose Alice chooses one of these different distributions and prepares an ensemble accordingly. So she prepares for many systems, each with a particular wave function, and she knows which wave function it is, and she has chosen this wave function randomly according to this distribution or that distribution. And about which distribution to use, she made a free will decision in the beginning. Now she hands over this ensemble to Bob with a challenge to empirically determine her choice. Which measure was it? Was it mu or mu prime or mu double prime? Okay, this is impossible for Bob. These ensembles are empirically indistinguishable. So now from this you can argue that there are facts in the world that we cannot determine empirically. There are limitations to knowledge. So nature knows what the right mu is, and we can't find out because we're in Bob's position. We try to determine it empirically, we can't. Okay, but that's just a side point. Let me get back to the main track here. So now, so far, I've talked about statistical density matrices. So far, there was no talk about fundamental density matrices or density matrix realism. Now I want to talk about Bohmian mechanics, because in Bohmian mechanics, you can see particularly clearly how the density matrix could have different roles and how it could make sense to have an ontic density matrix. So in order to understand that, let me first explain ordinary Bohmian mechanics. Here's the definition of the theory in the non-relativistic version. The theory says particles are material points that move around in space at every time t. They have a position qj of t, which is a point in three-dimensional space. And the motion is governed by Bohm's equation of motion. And this is basically equivalent to the equation that Owen showed you, except I have maybe a version here that also allows for spin. So here the wave function could have several components as it would have for spin. I think Owen's version was for complex valued wave functions. Okay, so here's the formula. The details of the formula don't matter much. It's just some kind of expression involving psi. You plug in the actual positions of all the particles. That determines the velocity, and that determines how the particles continue to move. The psi itself here evolves according to the Schrödinger equation. I wrote it down for the sake of completeness. Now, a basic fact, a basic mathematical consequence of these equations is that if at any time you choose the configuration, the positions of all particles randomly with psi square distribution, then at any other time it will also be random and it will also be psi square distributed. So this theorem is called equivariance. And we do assume that at the initial time, let's say at the initial time of the universe, it is chosen psi square distributed. And then it follows that at any other time, it will also be psi square distributed. So the equation of motion can be summarized in this way, with V, a particular vector field on 3 n-dimensional configuration space called the velocity vector field that's defined by this equation. Good. Now, if in an ensemble of systems, say 50% of the systems have wave function psi1 and 50% have psi2, then 50% of the systems, those with wave function psi1, have a configuration moving with velocity v psi1 and the other 50% with v psi2. So they have actually different velocities. So even if two systems, one belonging to the psi1 group and one belonging to the psi2 group, happen to have the same configuration, they will have different velocities. More generally, different distributions mu over wave functions, even if they have the same density matrix W, usually lead to different distributions over the velocities. Now, in Bohmian mechanics, you take the trajectories seriously. You believe that particles actually move according to these trajectories. So particles actually do have velocities, and there is a fact in reality, in nature, about whether the velocity was this vector or that vector. Now, if the wave function was this thing, then the vector was this. If the wave function was that one, then the vector is that. Okay, so nature needs to know what the wave function actually is in order to make the particle move the right way. Good. In particular, in Bohmian mechanics, the density matrix, the statistical density matrix of an ensemble, the density matrix alone does not determine the ensemble of trajectories. The trajectories depend on which wave functions you have. So it depends on the distribution mu, not just on W. So if Alice makes a choice between this mu and that mu, this mu will actually lead to different trajectories than that mu. Okay, so nature knows what the mu is, not just what the W is. So in this picture, what there is in reality is psi, not W. Okay, so that's in ordinary Bohmian mechanics. But now the situation can change if we change the defining equations of the theory. So here's a different theory. I'll call that W Bohmian mechanics. And let me tell you right away, it's a different physical theory. So it contradicts the ordinary Bohmian mechanics. In a particular universe, not both theories can be right at the same time, only one of the two. So if God creates a universe, he has to decide between these two different versions of Bohmian mechanics. So here's a modified Bohmian theory. These equations were first considered by Bell in 1980, but they were not seriously proposed. He considered it as a kind of counterexample. And they were more seriously considered then in the 21st century, as Owen already mentioned. So what I've written here is essentially, it's actually the same thing as Owen mentioned, just in a different notation. So here you assume that the equation of motion for the particles depends not on a wave function, but on a density matrix. So here, the density matrix is an operator, but you can translate it into a function of two configuration variables and two spin indices according to this kind of expression. And what you do here is, you take the trace over the spin indices, S and S prime, and you take the gradient with respect to one of the particles in one of the configuration variables, and then you plug in the actual configuration for both of the configuration variables. Okay, so there's some expression in which you can start from a density matrix and have it generate a vector field on configuration space in this way. And of course, you take the, or maybe not of course, so in this example of a theory, you take the density matrix to evolve unitarily in the usual way as expressed by this von Neumann equation. So the unitary evolution just amounts to saying that the time derivative is the commutator with the Hamiltonian. And then again, you can prove an equivariance theorem saying that if at any time, think of the initial time of the universe, you take the probability density of the configuration to be this expression here, which is kind of the analog of the psi-square distribution. It's what you have on the diagonal of the density matrix, and you trace over the spin components. If you have this distribution at one time, you have it at any time. So Owen also mentioned this fact already. So again, this is just a theorem for the unitary time evolution. Okay, so it's like you have a version of Bohmian mechanics in which the particles are guided not by the wave function, but by a density matrix. The equations are done in such a way that if the density matrix is pure, that is, if it comes from a wave function, then it just reduces to ordinary Bohmian mechanics, which in the following I will call psi-Bohmian mechanics. Good, so now let's compare psi-Bohmian mechanics and W-Bohmian mechanics. In psi-Bohmian mechanics, the state, which means the physical situation at any given time, is given by the pair Q and psi. Q is the configuration, the positions of all particles, and psi is the wave function. So the ontology consists of two things, of the particles and a wave function. Now in W-Bohmian mechanics, the state is Q comma W. The ontology consists of particles and a density matrix. So there is no wave function there. Wave functions don't exist in this theory. Except in the case if W happens to be a pure state, at least on the level of the whole universe. So the way I formulated the theory is actually a formulation that's kind of fit for talking about the whole universe, and having one set of equations that governs the whole universe, and then you could do some analysis. What would happen to subsystems? Well, basically what would happen is if the subsystems are suitably disentangled from the rest, they and isolated, then they follow themselves the same kind of equations, but if they interact with the environment, they do complicated things. Good. Next remark. How about density matrices then? Okay, in psi-Bohmian mechanics, you can use density matrices. You would use them in order to do to compute predictions, because you know the predictions, they don't depend on the actual mu, they only depend on the density matrix. But the trajectories do depend on the individual psi, and therefore, for an ensemble of systems, on the mu. Okay, so what's the status then of the statistical density matrix? It encodes incomplete information about mu. Good. It encodes the amount of information that you need in order to predict the statistics of outcomes, but not enough information in order to compute the trajectories. In W-Bohmian mechanics, the status of the density matrix W is that it is an object in nature, something fundamental, something real. So that's density matrix realism. If W is a non-pure density matrix, then the trajectories of W-Bohmian mechanics usually do not agree with those of psi-Bohmian mechanics for any particular psi. And another basic fact is empirical equivalence. So now consider psi-Bohmian mechanics with a particular probability distribution mu. So in order to make that explicit, I'll write mu Bohmian mechanics for that. Okay, so you have a random wave function psi, and mu is the distribution. Now let W be the statistical density matrix of mu. Then mu Bohmian mechanics is empirically equivalent to W Bohmian mechanics. Here's the proof. at any time t, the probability density of the configuration at time t, according to mu Bohmian mechanics, is this expression here. That is the psi-square distribution, which is the distribution of the configuration that you would have conditional on a particular psi. And in addition to that, you average that over all psis according to, well, what mu evolves to at time t. Now it's a kind of a mathematical exercise to prove that this agrees with this expression here, where W should be the what the density matrix evolves to at time t. And this is here what you have on the diagonal of the density matrix, again with spin traced out. So this is the analog of the psi-square distribution for density matrices. And this is, in fact, the same probability distribution. It's the same function of Q. Okay, so now you have these two theories. They give you different trajectories, but they have in common that at any time t, the probability distribution of the configuration at time t is the same thing. Okay, now if you wanted to do an experiment testing mu Bohmian mechanics against W Bohmian mechanics, well, at any time t, you would have to make a decision based on the evidence that you have at that time, and this evidence would somehow be in your configuration. But if the probability distribution of the configuration is the same in the two theories, you have no basis for making such a decision. So that means you have two theories which are completely and entirely empirically equivalent. There is no possible experiment, including all conceivable future advances, in order to decide between these two theories. Good. So what do we have so far? We have a theory that illustrates in a very clear and simple way how you could actually have a fundamental density matrix, how you could have density matrix realism. Now, this stuff with this equation of motion involving density matrices was actually not introduced for the purpose of making this point of density matrix realism, but for a different purpose, for the purpose of the conditional density matrix, which is a generalization of the conditional wave function. The conditional wave function in Bohmian mechanics is the following. Consider the case of complex valued psi. So spin 0, we ignore spin for a moment. Okay, so in the notation that I used before, this corresponds to the exponent k being equal to 1. The conditional wave function of a subsystem is the following. You take the wave function of the whole thing, which has first system, second system, X system, and Y system. And for the Y system, you insert the actual configuration. So the capital letters mean actual Bohmian configuration, whereas lowercase letters mean generic, the variable. Okay, so this means you have a function of two variables, X and Y. And for Y, you plug in the actual value of the Y variable, which is something that you have in Bohmian mechanics. Good. So this is called the conditional wave function. And this is often considered because it's the kind of wave function that you would attribute to a subsystem if you want to talk about whether the wave function of a subsystem collapses. That would be the conditional wave function. The conditional wave function does not in general obey a Schrödinger equation, except in special cases if it's non-interacting and not entangled. But it is actually always true that the velocity of the X system is given by the usual formula with just the conditional wave function, as in equation 1. Let me go back. What was equation 1? Equation 1 was Bohm's equation of motion. Okay, let me go forward again. Okay, Bohm's equation of motion, of course, applies to X and Y together, but you can also write the equation for X using just the conditional wave function using X alone. Good. Now, when you do have spin, so if your wave function has several components that corresponds to k greater than 1, then, however, this object, after inserting the actual configuration for y, has the wrong number of spin indices. There's still the spin indices for the y particles, but you want only a wave function for the x particles. Okay, so here is what you should do. You consider the conditional density matrix, which means you take this wave function, you form the density matrix for that, the pure density matrix. You insert the capital Y for the Y variable, and you trace out the spin index for the Y particles, which is called R here. Okay, which leaves you with a function of x and x prime and s prime, and that's called the conditional density matrix. So you can do a similar thing as the conditional wave function when you have spin, but you need a density matrix for that. And then your equation of motion expressed in this conditional information is exactly this equation 2. Let me go back. What was equation 2? Equation 2 was this version of Bohmian mechanics with an equation of motion in terms of the density matrix. Good, let me go forward again. Now, this kind of consideration is not limited to Bohmian mechanics. It's also an option for most theories which have local beables in 3 dimensions. Beables is a word that John Bell introduced for the variables that represent things that are real according to the theory. Okay, so in some theories, such as Bohmian mechanics or GRW, you have a clear idea of what you consider real. Okay, in Bohmian mechanics, it would be the psi and the q, the particle positions. So the local beables, the things that are in 3 dimensions, that would be the particle positions. Now, Owen already mentioned GRW theory. GRW theory postulates stochastic deviations from the Schrödinger equation. That is, collapse is introduced as part of the fundamental time evolution law for the wave function. In a simple version of that, the wave function at time t could be expressed in terms of the initial wave function at time 0 by applying certain collapse operators to it. So this L is an operator in Hilbert space that carries out a collapse on particle J at location X at time t. So this collapse could be thought of as the effect of an unsharp position measurement. So what GRW actually wrote down was multiplication by a Gaussian centered at X and with a certain width that is small on the macroscopic scale but large on the microscopic scale. Okay, so if you know what the collapse positions and times were, then you can apply these collapse operators to the psi 0. That gives you the wave function at time t. Of course, what these collapses, when and where these collapses occur is actually random. And GRW gave suggested a law for that could govern these collapses, a law for the joint probability distribution of all these collapses. Here I wrote down what this law is. It's given by the probability is given by this expression here, where L is an abbreviation for this product of these several collapse operators. Now, the GRW theory has been considered with different choices of ontology. In the so-called flash ontology, flash meaning you take certain space-time points to be material points. Flash because it kind of flashes up just for an instant of time and then it's gone again. So the local beables there are space-time points and maybe also associated with a label that that indicates the which particle it applied to. Now, with this theory, you can also do a modified version of GRW theory, a density matrix GRW theory. So this change is kind of not very difficult. If you think about it, how to do it, you would come up with the same formulas. You start with some density matrix here. You put these collapse operators in the right places. That gives you the joint distribution of all the flashes. You can also think of this this formula this way, that you take your density matrix and you have it evolve unitarily between these collapses. And when a collapse occurs, then you change your density matrix. You apply this collapse operator from the left and from the right. So you'd suddenly change your density matrix. So it's very similar to what you have in the version with a wave function, except you do it to the density matrix. You still have a stochastic evolution of the density matrix then. But you actually used a non-pure density matrix, which has the status of being something fundamental, something real. Nature, in order to carry out this kind of law, has to know what the density matrix is. Okay, so if God wanted to create a universe governed by WGRW theory, he would have to make a decision about what the initial density matrix is. So this kind of theory would also respect density matrix realism. And again, there is a theorem that this is empirically equivalent to the ordinary wave function-based GRW theory. If your initial wave function is taken to be random and and mu distributed, where the initial the initial density matrix W is just the density matrix associated with this particular probability distribution mu. And again, this is easy to verify because you just compute the distribution of the flashes. That is, you take this formula and average here over different psi's and then transform the expression into this formula. Okay, here's a slide about Gauss objection. Okay, so Shan Gao wrote a paper arguing that density matrix realism is impossible, that it is excluded by the Pusey-Barrett-Rudolph theorem, or PBR theorem. His reasoning was the PBR theorem shows that wave functions are real, so density matrices can't be real. W realism must be wrong. Okay, that is incorrect. So here, I just say explicitly, where is the mistake in Shan's reasoning? Well, if you write down more carefully what exactly it is that the PBR theorem says or shows, it's the following. It shows that if for every pure state psi, an ensemble of ontic states lambda is given, so you allow here a class of theories, okay? You're not referring to a particular theory, such as Bohmian mechanics or GRW. You allow a whole category of theories. Your theory can say what its ontic states are. They're called lambda here, but your theory is required to agree with the quantum predictions, with predictions for experiments. Okay, so for every pure state psi, the theory is required to provide an ensemble P index psi over the ontic states, and then reproducing the quantum predictions then can be written down as some equations. Certain probabilities have to agree with the usual quantum probabilities. Then PBR show, under certain reasonable assumptions, for any psi1 and psi2 different wave functions that are not multiples of each other, these two ensembles are disjoint. They're disjoint distributions in in the space of all ontic states. They don't overlap. Okay, now this fact, once you write it down clearly, it's obvious, does not conflict with the possible existence of other ensembles, P index mu or P index W over the ontic states that reproduce the quantum predictions for a particular mu or a particular W. Now, so that makes clear that there is actually no conflict between the PBR theorem and density matrix realism. Actually, it was also clear, once I wrote down W Bohmian mechanics, it was clear that density matrix realism is a consistent theory, okay? Now, there's perhaps another little remark that's interesting here, because you might think whether you could also do, once we're at it, once we talk about this PBR idea of whether these distributions are disjoint or not, you might wonder whether you could do something similar for density matrices, whether you could associate with density matrices ensembles that are disjoint, or whether you can associate ensembles that do overlap. Okay, so for PBR, the point was to show that it's not possible that they overlap. But with density matrices, of course, we know already that it is possible that they do overlap, because the usual idea, the most obvious idea would work. You just suppose that in reality there's a random wave function, and then of course there you can have ensembles of wave functions that overlap, even if your two density matrices are not multiples of each other, which for density matrices means they're not the same. Okay. So obviously, some ontic models allow that two ensembles with the same W overlap, so there is no theorem analogous to PBR for density matrices. Now, W Bohmian mechanics then shows the opposite, that it is also possible to have ensembles for different W's that don't overlap, and basically that just happens by assuming that there is in fact a fact in nature about what the W is. Good. Now a few words about statistical mechanics. Okay. First, before I come to the quantum case, let me talk a bit about the classical case. Okay, so there's Gibbs entropy and there's Boltzmann entropy. So let me recap what it is. So Gibbs entropy associates with every probability distribution over phase space R6n, value the Gibbs entropy, which is the integral rho log rho. And here is the Boltzmann entropy. Here x, capital X, is the phase point, a point in phase space. And what you do here is you take Boltzmann constant times the logarithm of the volume of this set, gamma nu. So here, what is gamma nu? Gamma nu is, I call that the macro set for some macro state nu. So Katie already had kind of a similar picture. That's because I also took this picture from Roger Penrose, who does very nice drawings. And here, the sheet is phase space. It's really 6n dimensional, and these cells here, these are the macro sets gamma nu. So what you do is whenever each gamma nu contains phase points that look macroscopically alike. Okay, so if two phase points even if they are microscopically, they have detailed differences. If they look macroscopically the same, they lie in the same in the same cell here. Now, these different cells are of very different sizes. Actually, the majority of the energy surface is taken up by the thermal equilibrium cell, of which we see only part here, and other macrosets are much smaller, and some here are even way smaller. Okay, so now these macrosets, they form a partition of the phase space. And so every phase point lies in exactly one of these macrosets. And you take, that is the gamma nu that you plug in here. So that gives you the value of the Boltzmann entropy. Okay, so now I need to talk about a bit about ensemblism versus individualism. Okay, so a review of a discussion of this this topic, this contrast, these two views is given in this paper here, of which I'm a co-author. So here's an example of these two views. What does it mean for a system to be in thermal equilibrium? The ensemblist would talk about a probability distribution for the system and would say, oh, a system is in thermal equilibrium if its probability distribution agrees with the thermal equilibrium probability distribution, or with a thermal equilibrium probability distribution. The individualist, however, would say, would not talk about probability distributions, but just about phase points, and would say, our system is in thermal equilibrium if its phase point lies in the set gamma equilibrium, which is this set here. You see only part of it. Okay. Likewise, the ensemblist would use the Gibbs entropy, or would tend to use the Gibbs entropy, and the individualist would take the Boltzmann entropy as the fundamental definition. Here, I should say, there are cases where the Gibbs entropy and the Boltzmann entropy agree, for example, in thermal equilibrium. Okay, so the discussion is more about which of the two is more fundamental, or what about cases where they don't agree. Now, okay, so as you may understand, I'm an individualist. A basic reason for being an individualist is that a classical system has a phase point, but not a probability distribution. It's not obvious what the probability distribution should be, what should be meant by its probability distribution. Okay, various proposals have been made. Okay, we can talk about that. Okay, but that is kind of the root of all the problems. Now, for the Boltzmann approach, which means the individualist approach, then the second law would mean the following. These macrosets have very different volumes, and phase points tend to move to larger and larger macrosets. So here you see a phase point that moves around in a kind of very complicated manner. Okay, and if you're in a very small macroset, you tend to move out of that, and then you're in the bigger one. And if you move around for a long time, you tend to reach the very big ones. This is the essence of Boltzmann's explanation of the era of time. Now, this works if you make the following hypothesis. Now, that's the past hypothesis. So here's my formulation of the past hypothesis. At the initial time of the universe, the phase point x0 of the universe is a typical point in a particular macroset gamma nu zero, which has very low entropy. It's a macro state with very low entropy. Notice here, there are some subtle differences. You see, I don't use the word probability. I'm not saying that the phase point of the universe was actually chosen randomly. I say typical instead, which is kind of the more accurate characterization of what is actually relevant. It behaves like most points in this set. Most phase points from this set gamma nu zero will actually have this behavior that in the future they move to larger and larger and larger sets, which corresponds to increasing entropy.
Can I just jump in? So we're at the time we had on the schedule. Can you
Okay,
Really sorry about that.
sure. I have one more slide. Okay, so let me say a few words about the quantum mechanical case. So the analog of the Gibbs entropy would be the von Neumann entropy traced W log W, and the analog of the Boltzmann entropy would be Boltzmann constant times the log of the dimension of a macro space, which is a subspace of Hilbert space. So instead of the partition of phase space, you would now have an orthogonal decomposition of Hilbert space into subspaces, each of them corresponding to a particular macro state. Now, in quantum mechanics, it would seem that ensemblism actually works much better than in classical mechanics for several reasons. I said in classical mechanics, the basic problem is that systems have an X. They don't even have a rho. Now, there are several reasons for thinking that they do have a rho or a W. One reason is, you see, psi-square distribution introduces some objective probabilities in configuration space. Well, that's perhaps not exactly the kind of thing that you want to have. It's not a density matrix, but it's also a density matrix you can get because subsystems of the universe have a reduced density matrix by tracing out their environment. And even in Bohmian mechanics, you can use the conditional density matrix. And that, in a way, represents the maximal possible knowledge that any observer could have about the subsystem. And on top of that, under density matrix realism, even the universe has a density matrix. So that sounds wonderful. And that is part of the reason why Owen wants to use a density matrix realism together with the von Neumann entropy. Now, I have reservations about that. Say the central one is that certain other difficulties with ensemblism remain. The basic one is that the von Neumann entropy measures how mixed the density matrix is, just like the Gibbs entropy measures how wide a probability distribution is. And it's independent of where it is. Like the Gibbs entropy, it doesn't matter where in phase space your probability distribution is as long as it has a certain width. You see some points in phase space, they correspond to big temperature differences between different parts of your system, whereas other correspond to having equal temperatures. Those with big temperature differences, they should have low entropy. With equal temperatures, they should have high entropy. But this is not reflected in the Gibbs entropy, and it's not reflected in the von Neumann entropy either. Okay, my last point that I want to make, how would you formulate then the past hypothesis in the quantum context? And then Eddie in his talk will, I guess, build on that and develop that thought further. So here's a formulation of the past hypothesis in quantum mechanics. The initial wave function of the universe is a typical vector in a particular macro space with very low entropy. Thank you very much for your attention.